Stripping down science. The Naked Scientists.
Hello, it's Sunday the 21st of August and we have liftoff, which is highly appropriate because on The Naked Scientist this week we're talking about aeroplanes. I'm Chris Smith and also here with us is Dave Ansell. Hello, Dave.
Hello. Coming up we discover how jet engines work and how aeroplanes alter the weather around airports, and also what engineers are doing about the noise planes make.
My university professor used to tell me that the noise of an FA Cup final crowd was enough to fry one egg, and the energy that's in the engine is very, very much more than that. We have been able to reduce the noise by 99.9% over the last 30 or 40 years.
But is 99.9% enough? Well, we'll find out shortly. Meanwhile, in the news this week, why scientists are forecasting improved spaced weather predictions thanks to a new way to spot sunspots a day before they happen, and how stem cells can be used to treat muscular dystrophy. So, if you've got any questions or comments for the show, get in touch now. You can tweet at Naked Scientists, write on our Facebook page, that's at nakedscientist.com/Facebook, or you can drop us an email. The email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with Chris Smith and with Dave Ansell, and we're in the deep end, or at least out into outer space. Dave?
That's right. Solar seismologists may be able to improve space weather forecasts. Now, the sun isn't something you look at very often, with good reason. It could damage your eyes. But we normally think of it as a uniform yellow disk. But actually, it's a very dynamic place with incredibly violent weather. Magnetic storms form on the surface, reducing convection and forming slightly cooler, so darker areas we call sunspots. Now, these would just be an interesting phenomenon if it wasn't for the fact these sunspots can develop into solar flares and coronal mass ejections, which are huge explosions on the surface of the sun, which can hurl high-energy particles out into the solar system. And if these hit the Earth, they can damage satellites, distort the Earth's magnetic field, and generate enough current in power systems to melt power transformers.
There is quite an amazing story going back to the 1800s, the mid-1800s, and the Carrington affair of the astronomer Richard Carrington, who was one of the first to spot the biggest sunspot ever spotted on the surface of the sun, which was associated with the sky turning red, and telegraph stations all over the world caught fire, people got electrocuted. It was an incredible sight, and it was all because of a massive sunspot.
It could be really quite serious stuff. So predicting this space weather is very important. And up until now, this has been based on what you can see on the surface of the sun. But Stathios Ioannidis and colleagues at Stanford University have been studying seismic waves on the surface of the sun, essentially sunquakes. Obviously, we can't put seismologists on the surface of the sun, but the SOHO spacecraft has cameras which are sensitive to tiny changes in the wavelength of the light given off. And this is due to the Doppler effect.
So they can see vibrations. So as the surface of the sun vibrates in and out a little bit, you see the light change its wavelength very slightly.
That's exactly it. And so by taking a kind of a snapshot of a big area of the sun, you can then build up a picture of how it's moving, and you can see seismic waves moving across the surface of the sun. Now, they've discovered that before a sunspot emerges on the surface, the magnetic field which creates it forms deep within the sun. And this rises up, and they discovered that this forms a series of kind of waves on the surface of the sun, which seem to be created about 40 to 70,000 kilometres down. And if you kind of work out their very characteristic pattern, and if you see them, you can predict that in about a day's time there's going to be a sunspot emerging on the surface.
So they're a sort of ripple which is presaging what's going to form there later. And at the time you've got those ripples, the sun isn't doing anything harmful. But by the time those ripples turn into a full-blown sunspot, then you could potentially have some trouble.
That's right. I mean, I think actually predicting whether a sunspot's going to produce a large coronal mass ejection is probably still something they're working on. But this obviously gives them more information to work on and a slightly more warning.
The obvious question, though, Dave, is it's all very well being able to predict these things, but if we can tell one is coming, what can we do about it?
Well, I mean, things like satellites can put themselves into modes where they're less likely to be damaged and less likely to be confused by strange signals coming from these particles, and power systems can be ready to flip the trip switches if you get big DC currents going around them and causing complete havoc.
Let's hope it doesn't happen again too soon. Not during the Naked Scientist, anyway. We don't want any havoc during our show. Now, interestingly, there's this whole question about trying to come up with new ways to treat diseases. And obviously, when you ask people, how should we do that? Most people say, well, we need to invent new drugs, come up with better ways to treat things. But what about all the drugs we've already got on the shelves? Are there any drugs lurking on the shelf that we think we can only use for one disease, but actually could be quite good for other diseases that we'd never thought of using them on? Well, there's a wonderful paper. It's been published in the journal Science Translational Medicine this week. It's by Joel Dudley and his colleagues there at Stanford. And what they have done is to take a very simple and very elegant logic, and they've said, OK, if we know what a certain disease does to the genes in a tissue, in other words, it might turn some genes on and some genes off, if we can find a drug which can produce the mirror image effect on the same or many of the same sorts of genes, then perhaps that drug will work on that particular disease and reduce its impact. So they wrote this simple algorithm and they used ulcerative colitis, a form of inflammatory bowel disease, as a good example of how to do this. And they looked at the gene profile of what happens in tissues affected by ulcerative colitis. And then they fed in a whole bunch of drugs, candidate molecules, and also some molecules that are used in ulcerative colitis to look at what the gene profile for those drugs was. And what they found was that prednisolone, which is a steroid, which is also the gold standard treatment for ulcerative colitis, was immediately plucked out by their system, so it was obviously working. But then up comes another drug called topiramate. Now, topiramate is used every day around the world, and it treats epilepsy. It was a direct match for the genes that go wrong in UC. It turns all the genes on or off in totally the opposite direction to ulcerative colitis. So they then said, OK, this drug appears to be having all of the right effects. Why don't we try it? So they got some rats, and if you dose rats with a certain chemical, you can produce the rodent equivalent of inflammatory bowel disease. So they did this in a group of animals, and then they dosed them with topiramate or with prednisolone, the current gold standard treatment for immunosuppression, and then they took another group that were just control animals that got nothing. And the topiramate-treated animals did as well, if not better, than those treated with the steroid. And the side effects from the topiramate are going to be less bad than the side effects from the prednisolone, because people often say that when you immunosuppress someone with the prednisolone, then although the disease symptoms go away, there are other side effects because you damp down the immune system and it can actually take the tissue longer to put itself right afterwards.
So is this going to be best for dealing with symptoms of diseases rather than necessarily getting at the cause? So it's a really good way of damping down symptoms.
I think it could actually be a range of things. I mean, you might be able to get to the mechanism behind certain diseases, but one thing that, when I read this, immediately jumped out at me was, what about virus infections? Because viruses are really hard to tackle with current drugs because they have to live inside our cells because they can't make new copies of themselves. They have to infect a cell. And that means discriminating with a drug between a virus and a host cell is really hard. So there are not many antiviral drugs. But viruses have to do things to the cell biochemically to put it into the right sort of mode to grow new viruses. So that means that the genes in those viral infected cells are going to get switched all over the place. So if you use this technique in that setting, you could find genes that have been turned on or turned off to prime a cell for a virus, and you could try and reverse it with some of the drugs we've got on the shelf for lots of other diseases, and you might find one that actually really deactivates some of these viruses really effectively. Maybe there is a cure for the common cold and it's lurking on a medicine shelf somewhere.
And then really, really slow down their rate of reproduction and improve things greatly.
Quite, you could turn the cell into something which is much less propitious as an environment for replicating that virus, which would give the immune system the helping hand. So, I mean, the point of this study is there are lots and lots of drugs which are on the shelves used for other conditions. With this very simple technique, you could quickly find hits against common diseases that drugs that are already licensed, they've already gone through all the agony of having very expensive clinical trials to find out what sorts of doses you can give, how safe they are, and so on. You could start deploying them in a whole new direction. So instead of having to reinvent the wheel with new drugs, you just use the ones that are already in circulation. Now, Duchenne muscular dystrophy, or DMD, is a genetic condition in which sufferers lack the ability to produce dystrophin, which is an essential structural protein in muscles. And this leads to muscle wasting and ultimately difficulty with walking and breathing. And the symptoms usually appear by the age of about 5. Duchenne muscular dystrophy could be treated by giving patients a healthy copy of that dystrophin gene. But the problem is that the gene is too big to fit into the viruses that we might normally use to add genes to cells. But now researchers in Italy have got around the problem by building an artificial chromosome to carry the gene into some cells and then adding this to stem cells, which can then be used to repair damaged muscles. And to tell us more, we're joined by Professor Giulio Cossu from the University of Milan, who's the scientist behind this work. Hello, Giulio.
Hi.
First of all, how common is DMD, Duchenne muscular dystrophy?
It's a quite common disease affecting approximately 1 in 3,500 males because the disease is linked to the X chromosome, so that only children are affected while females are carriers. They can carry the disease but not being affected themselves.
And the gene is monumentally big.
Yeah.
How big is big?
It's actually the largest gene known on this planet. It's larger than many bacterial entire genome, and so it's more than 2 million bases, which is the main problem for classic gene therapy, where the healthy copy of the gene is normally vehiculated through a viral vector. But this gene is too big.
So it's not simple to just add a new copy of the gene into the affected muscle cells on account of its size. So what approach have you been taking instead?
Well, the approach we took was to use a human artificial chromosome created in Japan by our collaborator Mitsuo Shimura, who has progressively taken away pieces of chromosome 21 and replaced the missing part with the whole dystrophin gene, with all its intervening sequence and regulatory sequence. So a sort of a mini chromosome that, however, is able to replicate every time the cell replicates its own chromosome. So it goes around every time that the cell divides and can carry the whole dystrophin gene inside the cells.
So you could put that chromosome into a diseased cell that lacks a healthy copy of the dystrophin gene. It would replace the unhealthy gene, make healthy dystrophin protein, and that should make the muscle function improve.
That's what we found in mice, but as you all know, everything is much easier in mice than in patients. And one reason is that the transfer of the artificial chromosome is inefficient, so that you need to select for the cells that took the chromosome versus all the other, many, many more, which did not. And human cells do not have, at variance with rodent cells, this infinite ability to proliferate in vitro. And therefore, immediate transfer of this technology to human cells is not possible and will require further technical steps to make this possible. That's what we're working on, and we hope to solve this problem in the next years.
Given that you can't just add the artificial chromosome directly to the muscle, what approach have you taken instead?
So we took this cell that we've been working for a number of years. They have a terrible name. I apologize. It's mesoangioblast. We weren't able to come out with anything better. Essentially, these are progenitor cells that are associated to the blood vessel, but we discovered that they are also able to make muscle if taken up from a biopsy of skeletal muscle. The cells can be grown in culture, and in the past we show that normal cells can be delivered through the arterial circulation and reach the downstream muscle. That leads to an even distribution of the cells through the downstream muscle. And in the past, we were able to show that this transplantation of this donor cell ameliorates the symptoms of muscular dystrophy in dystrophic mice and dogs. And at the moment, we have a clinical trial running, but the problem is that the strategy with donor cell requires two things. First, the patient needs to have an HLA identical donor, normally a brother, and this is pretty much like bone marrow transplantation. And second, this requires immune suppression, which is not a simple thing to do.
So a better way of doing it would be to take the person's own stem cells, their own mesoangioblasts, add your chromosome to them, and then put them back into the patient, and then they'd only be getting their own cells, and that would get around that problem, wouldn't it?
Absolutely. The problem now is that we don't have enough cells to do all these things. And so all these steps can be done with mouse cells, but not yet with human cells. So in order this to be tested on patients, this strategy still requires a few years of laboratory work.
And when you try doing this on mice, so if you take these mesoangioblast cells from the mouse and you put your artificial chromosome into them, can they improve the function of a mouse with muscular dystrophy and remedy its problem?
Yes, that's what we observe. After transplantation of these cells into the dystrophic mice, the morphology of the muscle ameliorated, the motility of these animals increased, even though it didn't reach the level of a normal mouse. So in no case we should talk about a cure, but just an experimental treatment that in preclinical setting is producing an amelioration of the symptoms of the disease.
Thank you very much, Giulio. That's Giulio Cossu from the University of Milan. Still work to do, but a wonderful discovery which you can find written up this week in the journal Science Translational Medicine. Dave.
Now, on a completely different subject, diamonds have actually been found in candle flames. The exact composition of a candle flame is actually very difficult to work out. It's a dynamic mixture of reacting gases, and it gets its colour from microscopically small particles of carbon. The problem is these particles are actively reacting, and by the time they've left the candle, they've reacted to form carbon dioxide or stuck together to form soot. So what exactly is going on in a flame has remained really quite obscure. Now, there's a really nice story about this. Professor Wuzong Zhu at St Andrews University was chatting to a colleague, and this colleague kind of, to make the point that we don't really know everything about science, said we don't actually know what's going on inside a candle flame. So Professor Zhu took this as a challenge and set about finding out what was actually going on.
Is he a chemist?
Yeah, he's a professor of chemistry, so he should have an advantage over most of us there.
So how did he do it?
Well, the big problem was extracting these particles from the centre of the flame quickly enough to stop the reaction. And he actually had to develop a new sampling technique, which involved using something called anodic aluminium oxide films, which are a piece of aluminium which has been oxidised electrochemically to form a honeycomb-like structure with holes. And you can control the size of these holes from a few tens of nanometres across to maybe 100 nanometres. And the back can be removed with phosphoric acid, leaving essentially a filter. He built a sandwich using maybe an 80-nanometre one at the bottom and a 40-nanometre one at the top. So the first one would filter out all the big particles, and the second one would catch the smaller ones. And he sort of dropped this into a candle for about a second and took it out really quickly. And then he studied these films using an electron microscope, and he found tiny pieces of graphite, as you'd expect, because graphite's a stable form of carbon at atmospheric pressure. He also found fullerenes, which are kind of different shapes of buckyballs. Then, very surprisingly, he found tiny diamonds, which shouldn't be stable at room pressure at all.
Wow, were they in the candle to start with, and they were just being released by the burning, or were these being made de novo?
Well, he thinks they were just being made. There's no diamonds in a candle to start with, so they must have been made in the candle in part of the burning process. They're actually very, very tiny. They're only maybe 5 to 10 nanometres across, so only a few tens or hundreds of carbon atoms across.
So not engagement ring category yet, then?
Yeah, I don't think your girlfriend's going to be very impressed if you give her a 4 nanometre diamond.
Unless she's a nano girlfriend, I suppose. But
I think those are probably quite rare. So this might not be ideal in that sense, but understanding how these diamonds are nucleating and being formed in a flame could be very important in understanding the growth of diamonds in something called chemical vapour deposition.
Because they are used and manufactured industrially, aren't they?
Yeah, they're starting to be made actually for gemstones. They call them cultured diamonds rather than fake diamonds because that sounds a bit more superior. But actually that's only a minor thing. The real thing is they're used for kind of surfaces on scalpel blades. They're used for heat sinks because diamonds are one of the highest thermal conductivity of any material out there, and possibly even for high temperature electronics which are trying to be developed. So if we can understand how this process is happening in a candle flame, it might go across to this chemical vapour deposition and improve the quality of the diamond films we can make.
Amazing. Out of a candle comes the answer to everything, it seems. Anyway, just to finish us off, candles are hot things. Well, here's something about heat, Dave. Climate change is driving animals uphill, it would seem. Now, over the last few years, I remember talking to various scientists who've been doing research on various animal groups, and there's been this idea that with global warming and climate change, certain species which can't tolerate the warmer weather, or pathogens that attack those species, which are flourishing more in the warmer temperatures are making animals migrate away from the equator to where it's cooler or go uphill to where it's cooler. But these are just sort of apocryphal stories or isolated cases. So what's been missing until now has been a really good unified view of whether there really is a mass migration taking place of various animal species around the world as things get warmer, because we have seen a global temperature warming signal for a number of decades now. So what scientists have done, this is Chris Thomas, who's a researcher at York University, he's got this published in the journal Science this week. What they've done is to say, OK, let's do a really comprehensive look at this. And they've done a really big study called a meta-analysis. And what this means is they take lots of individual little studies looking at lots of different species and they unite them all under one big study umbrella. And this is a way of ironing out the statistical noise in order to get a clear picture as to what is actually happening. So they take nearly 2,000 animal species and they look at how they have moved, both in terms of their latitude, away to or towards the equator over time, and also in terms of their altitude, whether they've gone uphill or downhill over time. And the result they find is really staggering, because what they find is an average uphill movement of 11 metres per decade. And get this, a distance away from the equator in terms of latitude of 16.9 kilometres every decade. So this is animals changing their average range over this timescale. And while they say that this is interesting, it's also much larger than the previous impacts that have been recorded before. And also, the other interesting thing to come out of this is that not all of the animals actually went with this particular result. There were some that bucked the trend. In fact, 25% of the species either didn't move or went in the opposite direction. Now, it's outside the scope of this study to explain exactly why, but then it's not really surprising, is it? Because if you've got some animals that are actually doing better in warmer conditions, perhaps they will migrate in the opposite direction. Or if you remove predation pressure, the predators are moving away because they don't like it where it's warmer, it leaves more niches behind for other species to occupy. So it's not surprising really that there are some animals that may not move.
I guess they could also be evolving and adapting to the change in temperature.
It would be quite rapid evolution, but you're right, and there are some animals that are just changing their behaviour to compensate. Birds, for example, are changing the time of year that they migrate at. But this is important because it shows that there really is a clear response amongst animal species to global change in temperatures. And it also has potentially clinical implications because, as emerging diseases specialists have been telling us for a number of years now, if you change the conditions on Earth, then certain animals are not going to be able to tolerate certain environments, so they will move. And when the animals move, the things that infect them move too, and you can end up with disparate groups of animals coming together in new ways in new environments, and therefore you can spread and share infections amongst them, including animals sharing infections with humans, which is where we think new emerging infections can come from, and we've seen this happen before. So it's certainly a space which is worth watching. Well, you can follow up on any of those stories if you're interested via our website. The references and transcripts of those items are there at nakedscientist.com/news.
Laying the facts bare. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Dave Ansell. In a moment, we'll be hearing how aeroplanes alter the weather around airports. Yes, you did hear that correctly. But first, carbon capture and storage. It's been seen by the government as an important way to reduce carbon dioxide emissions. The idea is that you capture CO2 emissions from industry and then you lock the gas away underground inside rocks out of harm. But what actually happens to the CO2 once it's down there underground? Planet Earth podcast presenter Richard Hollingham has been to the British Geological Society at Keyworth near Nottingham to meet scientists who are studying the process, including experimental geochemist Keith Bateman.
First of all, you've got your carbon dioxide gas, which is then compressed, so it's easier to pump along a pipeline the same way as you would do with gas or oil. You then pump it down a well into a suitable geological formation where the carbon dioxide will then initially start to dissolve in any water that's there, and over time chemical reactions will occur such that the carbon dioxide will then react with the host rocks and produce new carbon-bearing minerals which will permanently lock the carbon dioxide up.
Caroline Graham, you're studying the seal at the top of these areas where you're looking to inject carbon dioxide. Give me a sense of what you're doing, because you have this enormous cabinet in the centre of your laboratory, and a lot of tubes and wires I can see through the glass-fronted doors.
The big box is an oven which is designed to simulate the temperatures that the rocks would experience deep within the earth. And the tubes allow us to inject fluid into a sample of rock so we can look at how the flow processes will change with time.
Let's have a look inside the process going on. Whoa, the heat really hits you, doesn't it, as you open that up? It looks like a big saucepan or pressure cooker in the centre.
It is, yeah. So we are pressurising the material, but we're squeezing it with a liquid around its outsides, and that simulates how the rock would be squeezed in the earth. These two vessels on either side of it are used to contain the gas or the liquid CO2, which we then inject into the big pressure cooker, and seeing how easily the carbon dioxide will flow through the seal material. So what's the upper limit beyond which we can't pressurise the reservoir any further, so we know how secure it could be.
Well, Keith, we'll come through into the next laboratory. Let's just get a sense then of what is going on underground when you inject carbon dioxide. There's a cap and then there's, a reservoir?
A reservoir rock. Yes, I mean, what you'd use typically as a reservoir rock is a sandstone. Sandstones are naturally porous.
So you've got some in a bag here.
Got some in the bag here. This is a sample of some Sherwood sandstone. It's quite grainy. It's red in colour. You will see this all over the North Sea. In fact, we're quite lucky that the North Sea is a great area for storing carbon dioxide underground.
So you've got a cap, so it's not going to escape. But the other point here is that the carbon dioxide is not in there as gas. It will change over time, or the rock will change over time.
Over time, that gas will first of all dissolve in any water that is present. As the carbon dioxide dissolves in that fluid, it would actually make the fluid more dense, which will over time will allow the carbon dioxide to dissolve and reach out further and further into your reservoir.
Which is the point to bring in Chris Rochelle here. You can demonstrate this, can't you?
We can show this process in the lab with very simple lab experiments where we fill a tall, thin cell, a bit like a piece of double glazing, but thinner. We have a solution in that which is coloured. We put CO2 on over the top of it, and as this carbon dioxide dissolves, it changes the colour in the solution. And we can see fingers of carbon dioxide-rich water dropping down over time slowly through this solution. And we can compare this with computer models and computer simulations. Will they agree? Can we improve the models that we've got through simple lab experiments and then try and compare them to bigger systems and real injection systems?
Chris, you've got to be pretty sure you've got this right.
Absolutely. It's got to be safe, and you've got to have confidence that it will stay underground, both for public acceptance and regulatory and carbon trading arrangements. But we can look at natural systems, where carbon dioxide formed through natural processes is stored in certain rocks for millions of years. And in the same way that oil and gas are trapped and you get oil and gas fields, you can get fields of natural carbon dioxide. And we can look at these and say, what can we learn from those, and can we pick the best sites to store it in the future?
So where oil and gas came from, CO2 can go back. That was Chris Rochelle. He's from the British Geological Survey, and he was ending that report from Planet Earth podcast presenter Richard Hollingham. And you can find more from the Planet Earth team on our website at nakedscientists.com/Planet Earth. And this is The Naked Scientists with Chris and Dave. Now, we're talking about aeroplanes this week. Dave?
So first of all, we're going to have a look at how do jet engines actually work. One simple way to think about it is suck, squeeze, bang, blow. It's a great term. The engine sucks air in at the front, compresses it, then adds fuel which burns, expands and is blown out of the back, producing thrust and pushing the plane along. But to get a more detailed idea of the physics behind the jet engine, I went along to the Heritage Museum of Jet Engine Manufacturer Rolls-Royce in Derby to meet Professor Jim Wickerson.
We are in the business of creating thrust. We want to get hold of air, throw it behind the engine. As we accelerate it out of the back of the engine, we're going to have a reaction force. That reaction force is going to push the engine through the sky. The engine is attached by a pylon to the aircraft. So in the action of pushing the engine, we're going to pull the aircraft through the sky. An aircraft wouldn't move without being pushed.
So this is essentially the very, very basic physics, Newton's second law.
There's more to it than that, but Newton is a very good start. In order to accelerate this air through the engine, you have to apply a force to it. The thing which is applying a force to this air to accelerate it out the back of the engine is the engine. And then Newton said in his laws that if you apply a force to something, the air, then the air will apply an equal and opposite reaction to the mechanism which is doing this. And that mechanism is called an engine. And then provided we attach the engine by struts, which are strong enough to do the job, but not too heavy, then this engine will pull the aircraft through the sky. And that sort of engine is called a gas turbine engine.
I guess virtually any aeroplane engine must work on this basic principle because there's nothing else to push on in the sky other than air. So what actually is special about the gas turbine, or what we normally call a jet engine?
The special feature is the higher speed jet, which lets us fly faster. So how does it work? What we have available is fuel. Fuel, kerosene, is a very condensed form of energy, and we can convert the fuel to this fast-moving jet, which is going to give us thrust. We then have what's called a heat engine. There are car engines, those are heat engines. There's jet engines, those are heat engines. What they do is they take the fuel and they burn it. If you did that burning at ambient pressure, we'd be stuck with the thermal energy. We burnt the fuel, we've now got some hot air, and all we would have done is heat the house or heat the room. The characteristic of all jet engines, car engines, piston engines, whatever, they first of all have a compression stage where the air comes in and gets squashed. We then have a combustor where we burn the fuel, and then having squashed first in the compressor, we can then expand the combustion products through turbines which drive compressors and then out through the back of the engine. Because we're expanding, we're getting cooler, and we're converting some of the thermal energy we created in combustion to the thing we want, work to drive compressors and work to accelerate a jet out the back.
So is it essentially easier for the air to get out through the turbines at the back of the engine than back through the compressor forwards?
Okay, so why does the air go out through the turbine? The air has first of all got to be squashed. Yep. If we don't squash the air before we do the combustion process, we'll never later on be able to expand the air and convert some of the thermal energy we've built up by combustion to something useful. So we must squash first. So we have the rotors and stators, these airfoils of this axial compressor, pushing the air up the hill of pressure. We then have a burning phase where the gas stays at the same pressure but gets much hotter. We then drop the air down through the turbine. We're dropping pressure through the turbine. If you give any gas a pressure drop, then it's going to experience a force to accelerate it. If pressure is dropping, the air is going to go faster into the place of lower pressure. So we have a pressure drop through the turbine, and in that pressure drop, the gas goes faster. The fast-moving gas is aimed through nozzle guide vanes at moving turbine blades. The fast-moving gas pushes the turbine rotor blades, and they're connected by a shaft to drive the compressor. Now, why is the gas going in that direction? Because there's a pressure drop. If there's a pressure drop, the air will follow the direction of the pressure drop. So we're now dropping pressure through the turbine. The air is accelerating, pushing turbines, driving compressors.
So why is the pressure actually dropping as you leave the engine?
Well, pressure drops twice. There's a pressure drop through the turbine. The turbine is the thing which drives the compressor. There's another pressure drop through the nozzle. Why do we have pressure drops? Because we have to. You can't get something going fast to then push against a turbine unless there's a force. The pressure drop multiplied by the flow area is the accelerating force. So we must have a pressure drop through the turbine to get the very fast-moving flow which pushes the turbine. Now, the way we get a lot of force on one turbine, so we don't need many turbines, is by having the gas going very fast. Typically, through a Trent engine, at takeoff, we've got 200 kilograms a second of core flow. We accelerate that 200 kilograms of core flow to 1,000 meters a second, or 2,000 miles an hour. As we get that fast-moving flow, we impact it onto the turbine blades, and as we turn through the turbine, we get a lift force of about 20 ton force. So that's a large force on one turbine, so we don't need many turbine stages to drive the compressor. They actually travel at the speed of sound, these turbine gases, and it's the speed of sound of a hot gas. You may know that the speed of sound in air is 330 meters per second. We've got a hot gas, so the speed of sound is 3 times as much. So we're travelling at about 1,000 metres per second. That fast-moving flow would only go fast because there's been a pressure drop.
So your gas turbine is producing this immense amount of power. Even on a plane, are you just extracting that by the air accelerating out the back of the jet itself?
OK, well, that takes us on very nicely to turbojets and turbofans. What we talked about so far has been a turbojet. So in the 1960s, we invent the turbofan. We add a low-pressure turbine, a low-pressure windmill, downstream of the first turbine. That low-pressure turbine drives a huge fan at the front of the engine. The huge fan builds up a little bit of pressure with a lot of air and throws a large mass back at a low velocity. Having gone through the low-pressure turbine, the core air has used up most of its spare pressure and again just pops out at a modest velocity. So we've added complexity, we've added cost, we've added weight, we've added engine drag, but we've doubled or trebled the amount of thrust for a given amount of fuel and hugely reduced the noise, because jet noise goes with jet velocity to the 8th power. So as we drop the jet velocity, the noise plummets. If you've ever been sent to listen to a A380 taking off on a radio programme, you get into a mess because they're so quiet you can't hear them.
And we'll be hearing more about reducing jet engine noise later on in the show. That was Professor Jim Wickerson, a specialist in gas turbines at Rolls-Royce.
Dave, did he say 200 kilograms of air in the engine per second?
Yeah, absolutely incredible, because that's 200 cubic metres of air every second.
Passing through that engine.
They're really, really serious pieces of kit.
They certainly are. Well, if you're interested in finding out a bit more about how jet engines work, we've actually made a very fun episode of the Naked Scientist's Scrapbook, which is both on our website and as a podcast and on YouTube. If you look up Naked Science Scrapbook, you'll find it. And that explains in step-by-step nice cartoony drawings with a lovely description by Sarah Castor Perry how a jet engine actually works in easy steps. So look it up on iTunes or go to nakedscientists.com/scrapbook. Now, current estimates suggest that there are over 500,000 people airborne around the planet at any moment in time. Quite a staggering figure, that, isn't it? Inevitably, some of the aircraft who are carrying those people will be passing through clouds. And recently, researchers have shown that this can cause a very strange phenomenon to occur. Holes open up inside the cloud, and the contents of that hole fall out as rain or snow. And Dr. Andy Hamesfield from the National Centre for Atmospheric Research made this discovery, and he's with us now. Hello, Andy.
Hi, how are you?
Very well, thank you. First of all, tell us, what actually is the cloud phenomenon that you've been looking at? How would people recognise it?
So this started back in the late 50s and actually 60s, but with more and more aircraft flying, these features have become more apparent. And the most obvious examples are fairly thin cloud layers, mid-level clouds like 5 kilometers to 7 or 8 kilometers, and what they appear to look like from observers at the ground, from photographs and people observing from the ground, is basically just like circular hole inside of this thin cloud. So the cloud is surrounding the hole, and often, almost always, snow or even rain down lower is observed falling out of the layers.
Was there debate over whether aeroplanes were actually causing this phenomenon, or was that always a given and we just didn't understand why it was happening?
The thought was early on that these were either meteorites burning up cloud, or maybe they were rockets, or even more recently, there are observations that look like maybe they're flying saucers in clouds. A spectacular example of that occurred a year and a half ago in near Moscow and Leningrad, I believe, and it looked basically like a flying saucer. But what I believe it was precipitation falling out of a deeper cloud layer, so you couldn't see the hole because it was covered over the top by cloud, but had this feature that looked almost like a flying saucer.
So how did you step in and try and understand what was actually going on in these clouds with these funny features?
Well, the first thing that we just coincidentally noticed was 4 years ago we had a project in Colorado flying our organization's research aircraft through clouds to study their properties. And we made the observation that we inadvertently flew through a snowband which looked like it was produced from one of these holes. And it turned out we went back and identified the two aircraft which actually flew through that cloud layer, and they turned out to be two turboprops. And then, but we actually could measure the contents of this precipitation, and that led us to expand the study to what looked like possibly not only turboprop or turbine or propeller aircraft were inducing this effect, but jet aircraft as well. So we had a spectacular example in this study we did in the last year of almost 100 aircraft which were generating little lines, but some narrow lines, maybe 2 or 3 kilometers across. Some were reaching 200 kilometers across, of holes in clouds over Texas.
So what you were effectively doing was marrying up flight data, where the aeroplanes were, with observations of these features, presumably from satellites, in order to say, look, the planes are present at the scene of the crime every time, so we can be reasonably sure that planes are triggering this thing to happen.
That's right. Possibly not every time, but these circular holes are just giveaways. And so what we did was, the first thing, we went to this terrific satellite image with 100 of these holes, these little lines in them, identified the aircraft as being both jet aircraft and propeller aircraft, turboprops, every aircraft you can imagine, military. So we identified the aircraft, and then the next question we had is, how long do these features last? And because think of an aircraft as just being a little pencil line through a cloud, and yet these holes are visible in satellite imagery and elsewhere. And so we decided, okay, we would like to study this effect. So we used probably the most sophisticated weather research forecast model, which is developed at my organization, National Center for Atmospheric Research, and used that model with the same type of conditions, thermodynamic atmospheric conditions, that were present in that terrific case that I just referred to. And we were able to actually model the mechanism by which these holes were produced.
What is the mechanism behind this then? What actually causes the aeroplane to make these phenomena occur?
Around the tips of propeller blades for propeller aircraft and for turboprop aircraft, there is expansion of the air. That's the engines pushing back behind it. The expansion process, as we know, causes cooling. And cooling then can cause cloud droplets, which are at the ambient temperature, anytime they're below about minus 10 degrees centigrade, to cool to the point where they spontaneously freeze at minus 40. And this is a well-known phenomenon of spontaneous freezing. It's just that the aircraft, just like weather modification activities, act as a nucleus. They provide ice crystals, and these crystals then seed the cloud. Now,
so does this only apply to a subset of clouds? Because I would think that clouds that are quite high up in the air will already be at that much lower temperature. So will this be clouds closer to the ground then?
Well, it could be clouds in the middle atmosphere in the summer. They're at the temperatures where this process can occur, which is where almost all of the sightings of holes in clouds have occurred. But in the wintertime, where there's thicker cloud, perhaps often near the surface in a actual large percentage of cases in mid-latitudes, then this effect can occur at low altitudes, and you wouldn't necessarily see a hole, but there is precipitation that will be formed when temperatures are below minus 10 C.
So the plane goes into the cloud. In the case of propeller-driven aircraft, you get zones of low pressure around the tips of the propellers. Do you get the same phenomenon caused by jet planes because of the wingtips, which have their associated low-pressure regions around them?
That's absolutely right. And so, again, that low pressure is correlated with, is due to expansion of air, and that then has the effect of cooling cloud drops at their ambient temperature down to as low as minus 40 C, where they spontaneously freeze. So it really opens up almost any type of aircraft to this process, and we have documented this for just about any type of airplane.
So what actually happens once the hole has got seeded, so the aircraft has gone through, it's created the optimum conditions to make one of these holes on its way through, does the hole then grow? Because as you recruit more particles in and you get downdrafts as the particles fall out, do you then get more stuff coming in to replace it that then itself turns into more ice particles that drop out?
What happens is that the process of going from cloud droplets to ice crystals liberates heat. And as those crystals continue to liberate heat, they generate, just like a cloud, there's buoyancy, and that causes rising in the center and cooling or subsidence, subsiding air, and evaporation of cloud drops on the edge. And even though it's just maybe one burst of particles, this process can and is self-sustaining. We've documented 2 hours or more following passage of an aircraft that these holes are still observable.
And how big do they become?
We have documented 6 to 10 kilometers from a little pencil slice through a cloud from an airplane.
So given that you've got this phenomenon, you can put the aircraft at the scene of the crime, we know they're doing it, is it actually a meteorologically significant impact? In other words, how much water is the cloud robbed of in terms of its precipitation potential? And if you summed all of the impacts of this around the world, is it important?
It's not important in a global scale, but where it might be important is in the wintertime in mid-latitudes with busy airports. So airports like Heathrow, Frankfurt, De Gaulle, O'Hare in the U.S., those airports which have considerable amount of traffic, those clouds can be continuously seeded in the winter where there's low cloud.
And what sort of volume of precipitation are we talking about? Is it significant over background?
We have documented a case in Colorado where, at an airport in Colorado, where the precipitation rate is up to 5 centimeters per hour. And if it lasts over that spot, if there are lots of airplanes flying through, we're talking about 5 centimeter per hour rates under conditions where there's a lot of aircraft traffic, especially on climb out.
And are there any other things that we can learn about cloud science or atmospheric science on the basis of what you've discovered?
The most interesting thing is that we are able to document what's called dynamic seeding, and in many of the earlier cloud seeding attempts, tried to invigorate clouds by dynamic seeding, where they put ice in the cloud at a certain point, and they hope that the ice grows and causes these updrafts and downdrafts that are around the edges, or circulations. And this is a good example of this process, and we're able to model it.
Andrew, thank you very much. That's Andrew Hamesfield. He's from the National Centre for Atmospheric Research. And if you want to follow up on some of Andrew's work, you can read the paper he published on that phenomenon earlier this year. It was in the journal Science.
Distilling the best science. The Naked Scientists.
It's The Naked Scientists with Chris Smith and with Dave Ansell. We're talking about the science of flight this week.
So far, we've heard how aircraft can impact on climate. But there's also a major impact much closer to the ground, and that's the noise they make. And as air traffic grows, it's becoming an increasingly important problem. So to find out what manufacturers are doing to solve the problem, Ben Valsler's been to speak to Rolls-Royce's senior project engineer, Joe Walsh, and their chief noise specialist, Andrew Kempton.
Aircraft noise has been a problem since the introduction of jet-powered aircraft in the late 1950s, early 1960s. It can be a serious problem for those living close to airports, and it restricts airport growth and the growth of aviation because of high noise levels.
So what's actually causing the problem? Is it the engines? Is it the movement of the aeroplanes themselves? What are the issues that we need to focus on to try and solve this problem?
Engine noise has been the principal culprit, but over time the noise levels we've managed to reduce significantly from the engine, so that means that other noise sources on the aircraft, are becoming now to be serious concerns. The noise of the airframe itself, without engines, the noise of the aircraft as a glider is a significant contributor to the noise when the aircraft's coming into landing.
So, taking the engine itself, what is it about that engine that creates so much noise?
Well, when you consider that the engine is providing thrust for the aircraft, and the way it does that is to suck in air, accelerate and pressurise it and exhaust it, that provides the forward thrust. So one of the sources of noise is created by the air exhausting, creating turbulence, creating noise. But as engine designs have developed, we've gone to larger fan diameters, which suck in more air, exhaust the air more slowly, and so generate less noise, which is good. But also the fan is there creating noise in its own right. So although the overall noise is reduced, we now need to consider the noise from the fan and other what we call turbomachinery components and find ways progressively to reduce those noise sources.
Jet engine designs have changed over the last 50 years, presumably with the main aim to get more power for less fuel and be able to lift more weight and stay in the air for longer. Has reducing noise been a consideration throughout that development?
Oh yes, entirely. We've had a significant effort into noise reduction at Rolls-Royce for many years, as have the other engine manufacturers and the aircraft manufacturers. And although we've been quite successful in achieving significant noise reductions, there's still more to do. So the effort will continue, but the nature of the challenge is changing as we've progressively reduced the traditional noise sources. Other noise sources come along and we need to continue to address those, looking at the problem as a total system problem.
So, as well as the inevitable noise of having to push a lot of air backwards quite quickly, what other parts of jet engines make noises? What other designs can we put in place that can cut down some of that noise?
The fan noise, which is generated by interactions between the fan and hardware behind it, can be reduced by careful design of the fan, where we're using computational methods, very big computers, to assess what noise is created and to minimize that at the same time as ensuring the fans are very efficient. But we also have acoustic liners, which we line the ducting of the engine, which help to absorb the sound.
So it's not just about reducing the sounds that are created in the first place, but it's about managing how they then travel away from the engine so that we can reduce how much actually gets out into the environment.
Yes, and there are even some designs which try and use the airframe itself to shield the noise coming from the engine, to ensure that that noise doesn't get down to the communities around airports.
What difference have we been able to make so far?
Well, only a small amount of the energy in an engine actually comes out as noise. My university professor used to tell me that the noise of an FA Cup final crowd was enough to fry one egg, and the energy that's in the engine is very, very much more than that. So we have been able to reduce the noise by 99% or 99.9% over the last 30 or 40 years. But unfortunately, the human ear does not respond linearly to changes in acoustic energy that's reaching it. So although we've reduced the sound power to 0.1% of what it used to be, this is only represented by perhaps a factor of 8 reduction in annoyance of people listening to the aircraft. But considerable strides have been made, and work is continuing to drive down noise further.
I imagine that there are other things that we can try and do. For example, make the engines powerful enough to take off very quickly, or to perhaps reduce the length of runway that they need so that actually they're closer to the ground for less time. Is this something else that we consider as well as the noise that the machine itself makes?
Yes, because ultimately what we're trying to do is to reduce the annoyance received on the ground, and there are many factors which cause annoyance. Not only the sound intensity, but also the character of the sound, what frequencies are present, how long the noise lasts for. So when you're considering how to mitigate those things, factors such as aircraft performance, thrust required to take the aircraft off the ground, are all variables, and they're considered as part of the initial design concept evaluation to look at the most effective way of meeting all of the aircraft requirements and all of the engine requirements, including reducing noise.
I assume that everything has to be a bit of a compromise. We can't purely aim for a very quiet engine that actually produces a huge amount of CO2, and likewise, we can't aim for a super efficient engine that will deafen people nearby.
Yes, design trades are evolved. It's useful sometimes to look at what it would take to design a very quiet engine. So we were involved with some work called the Silent Aircraft Initiative, and that looked at what it would take to design a functionally quiet aircraft that would be imperceptible above typical background urban noise levels. And that aircraft looked a bit like a flying wing. It had exceptionally low projected noise levels. It had significant technical challenges associated with it, but in terms of an extreme design, it did show that measures could be taken to generate very low noise levels. However, there was a downside. The downside is that the lowest noise design doesn't coincide with the best performance design. So inevitably there is some balance required, and what we're looking to do is to achieve low acceptable noise levels whilst designing an aircraft which meets many other requirements: operational, safety, economic, emissions, chemical emissions as well. And we're part of that design trade, and we're developing noise technologies that allow the best possible progress on noise reduction whilst allowing progress to also be made on other attributes.
That was Joe Walsh, and before him, Andrew Kempton, both from Rolls-Royce, speaking with Ben Valsler.
And you're listening to The Naked Scientists with Chris Smith and with Dave Ansell. We are talking about the science of flight and the impact of air engines on the environment and so forth this week. Questions coming in. Titus Teresa, Dave, this is a great question, says, how does a jet engine actually get started in the first place?
A gas turbine jet engine is quite interesting in that it just doesn't work unless it's spinning like a normal car engine. So basically you've got to spin it up fairly fast. So you attach an electromotor into it, either it's integrated in there or you stick it on the outside and spin it up. And then it gets going pretty fast. You then inject some fuel, then you essentially have something like a kind of hardcore spark plug inside it, which ignites the fuel, then it starts everything going, and it basically then starts running, spins up to full speed, and you have a jet engine.
So it's not dissimilar to a diesel engine in the sense that you've got to get the engine spun up to start compressing air to get it hot so you can inject fuel to start it burning, and then once it's going, it's got its own ability to carry itself.
I mean, yeah, pretty much. And also, essentially, there's nothing really to make the explosion coming out the back if the air's not coming in the front. So you've got to have everything spinning for it to work at all.
Now, Jonathan Urbach has said on Facebook, do contrails cool the atmosphere? And he's talking about effects in temperatures measured around September the 11th, 10 years ago, when there was a big reduction in the use of aeroplanes, obviously, and there was a corresponding change in temperature.
I think there have been some studies done on this. I think there's one 3 or 4 years back, and I think they can either increase the temperature or decreasing it depending on where they are. If you're in somewhere very, very sunny, then they can actually reflect out more than reflect back in. But I think on average, they reckon, especially places like the UK, they tend to actually heat up the Earth more because they're acting as an insulating blanket, as cloud does, and so they actually, if anything, increase the global temperature.
Now, we've heard on Twitter from Drugs Worker, he tweeted at Naked Scientists, are big planes damaging the ozone layer? And if so, will we have better engines that don't do this in future? I mean, obviously, one thing we've got to bear in mind is big planes are going to pump out a lot of CO2, and CO2 will increase global temperatures, and at higher temperatures, I think the equilibrium is shifted in favour of making less ozone and degrading more ozone, so you net have less ozone.
And I think actually if the plane's flying through the stratosphere, so like Concorde was, then just I think pumping water in there can form little ice crystals, which are very bad for ozone. But lower down, I don't think that's a big effect.
So the height is the important thing?
I think that's certainly a very, very important thing.
But presumably quite small in comparison with CFCs, chlorofluorocarbons, the things we used to put in fridges, which are known to be terrible for ozone.
Yes, and I think essentially the planes aren't up. There aren't many planes up in the stratosphere flying around, especially now since Concorde's given up the ghost.
Thank you, Dave. And just as an aside, we heard from Jeremy Baker, who said on Facebook, there is a lovely photo on yesterday's Optic Picture of the Day. If you go to at Optics, that's atoptics.co.uk, and look at the Saturday 20th of August picture, you'll see a really nice picture of a hole-punch cloud that Andy was talking about earlier. Right, it's now from one set of questions to another. harder question. Here's Diana O'Carroll with our question of the week.
This week, Jerry Hirschman asks, how does one sail in the sun?
Hello, Naked Scientists. There's been a substantial amount of discussion recently about solar sails. I'm curious to know by what mechanism a photon, which is massless and has no electrical charge, imparts momentum to a solar sail.
If light is supposedly massless, then how does it apply force to a sail?
Hi, I'm Dr. Natasha Hurley-Walker, a fellow at Curtin University in Perth, Western Australia. To answer your question, in 1871, James Clerk Maxwell predicted that electromagnetic waves would exert a tiny but measurable force on a surface, and this was experimentally verified in 1899 by Pyotr Lebedev. One can integrate the electromagnetic wave equation and show that for an incoming wave, the exerted pressure is equal to half of the energy density of the wave. Or, as shown by Einstein in his theory of special relativity, one can think of light as particles, i.e. photons, which have momentum. This is equal to the energy of the photon divided by the speed of light. Therefore, when a photon is reflected or absorbed by a surface, it imparts some momentum to that surface. This is called radiation pressure. Solar sails utilize radiation pressure by combining the imparted pressure over a very large surface area. At Earth's distance from the Sun, this adds up to about 1 micropascal of pressure. Solar sails typically have 20 to 30 square meters of collecting area, but some proposals have been made for designs with half a square kilometre of collecting area. The pressure is small, but with a low-mass sail deployed for a large time, solar sails can build up to large speeds while using no fuel.
Given that photons are particles, when they hit a surface they do impart a bit of momentum upon it. So this radiation pressure can get the sail moving, and, over time, a large enough sail will have your spaceship moving very quickly. And at least there's no risk of capsizing. But next week, what's that horrible smell?
Hi, I'm David from London. I wondered if you could tell me, why do wet dogs smell?
Always blame the dog when there's a bad smell. But where does it come from and why? Answers to Chris at thenakedscientist.com. You can Facebook us. You can write on our forum, which is at thenakedscientist.com/forum, or you can Twitter at Naked Scientists.
That was Diana O'Carroll with our question of the week. If you know what gives wet dog that distinctive smell, get in touch.
Thank you very much, Dave. That's it for this week. Thank you to Julio Kosu, Jim Wickerson, Joe Walsh, Andrew Kempton and Andrew Hamesfield. Production this week by Emma Stoy, Amy Chesterton, Ben Valsler and Tom Simpkins. Next week it's Science in Scotland. I'll be up to find out about cannabis-like chemicals that lack the side effects and a woman who's made a maze for yeast. Join us next week if you can.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.